Good day, viewers. Welcome to Toydel online class. So yesterday we started indices. Indices. We started this topic yesterday, and I was able to give the laws of indices. I gave about 7 laws yesterday, and we considered 3 examples. Though we were able to solve 2, but we are left with 1. But before I continue today, I would love to do a kind of recap of what we discussed yesterday. So indices, we started by saying if you have x times x times x times x, that is x in 4 places raised to power 4. That is, indices will enable us to be able to abbreviate this type of problem. So where we have x raised to power 4, this x is called the base. Then this 4 is called the power, or we call it exponent. Exponents, or it is called index. And index is singular, while indices is plural. So where we have x raised to power 4 is the shorter form of writing x in 4 places. That is just the little introduction about indices. Then I want to go to the laws of indices. We have about 7 laws of indices. About 7 laws of indices. The first one is when we have x raised to power a times x raised to power b. That is, they must have the same base, but they can have the same power or index or different power of index. So if the operating sign is multiplication, the law says that we should add the power together, a plus b. And this is the first law of indices. For instance, e.g., for example, if I have 2 raised to power 3 multiplied by 2 raised to power 4, then if I want to apply the law, I'll pick 2. The operating sign here is multiplication, so I will add the power 3 plus 4, and that gives us 2 raised to power 7. And of course, 2 in 7 places, that's the, let's say we have 4 times 4, 16, 64, that would be 128. That is what we are going to get. So, and the second law that we discussed about says that if you have x raised to power a divided by x raised to power b, the law says that it will be x raised to power a minus b. That is, in this case now, if the operating sign in between the two is division, then the law says that we should subtract the power. E.g., for example, if I have 5 raised to power 4 divided by 5 raised to power 2, according to this law now, we are going to get 5 raised to power 4 minus 2, and that will be 5 raised to power 2, which is equal to 25. So that is the second law that we discussed. I just want to do a recap of what we have discussed yesterday before we continue today. Then the third law says that if you have x raised to power a multiplied by b, the law says that it's the same thing as you saying x raised to power a b multiplied by everything. That is, e.g., for instance, if you have 2 raised to power 3, everything raised to power 2. So this is the same thing as you saying 2 raised to power 3 multiplied by 2. We are going to multiply the 2 powers, the 3 inside and everything over 2, and that will be 2 raised to power 6. Then the fourth law that we discussed is that if you have x raised to power 0 is equal to 1. That is, anything raised to power 0 is 1. E.g., if you have 1000 raised to power 0 is 1. So anything raised to power 0 is 1. And there's this fifth law that we discussed yesterday. It says that if you have, the fifth one says that if you have x raised to power minus a, that is, if the power attracts a negative sign, then this is the same thing as you saying 1 all over x raised to power a, that is the reciprocal of x raised to power a. So this negative, if you want to write it in positive form, this is what you get, and vice versa. So, e.g., if you have 2 raised to power minus 3, this is the same thing as saying 1 all over 2 raised to power 3, and that's the same thing as 1 all over 2 in 3 places is 8, and that will be the answer. So then the sixth law that we talked about yesterday is talking about The sixth law is talking about when you have either square root, cube root, quart root, or and what have you. That is, if you have x raised by 1 all over a, the law says that this will be a root into x. That is, where we have this a, if it is 2, then we are talking about square root. If it is 3, it is cube root. If it is 4, it is quart root. And if it is n, it is the nth root of what we are given. So, e.g., for instance, if you have 3, let's say if you have 9 raised to power half, then this is saying that this is square root of 9, and that gives what? 3. And I don't want us to be rigid when it comes to this sixth and seventh law, because we can actually use our common sense and actually get the answer without even going through this law. Because if I decide to change 9 as index of 3, that is 3 times 3 is 9. So if I change this to 3 raised to power 2, multiplied by the half, this will take care of this. Then at the end of the day, I'm still going to get my 3. So this law, the laws of indices can actually guide us. But there are times that it is not compulsory that we follow the law to letters. That's what I'm just trying to say. That at times we should be flexible and don't just depend on the law. So the last law that we talked about yesterday says that if we have x for b all over a, that is, in this case, we have the 8th root of x, then b squared. That is, this is what we are going to have. We are going to have the 8th root of x, everything raised to power b. That is the interpretation of that law. That is the interpretation of that law. That is, we have x raised to power b. Okay. So like this seventh law, for instance, if we have, e.g., if you have something like 4 raised to power 3 all over 2. So in this case now, of course, we know that this 2 there now is talking about square root. Then everything raised to power 4, that is, we are going to have, this is the same thing as you saying square root of 4 raised to power 3. And that's the same thing as you saying square root of, what is 4 raised to power 3? 4 in 3 places, 4 times 4 times 4, that will be 64. Then what is square root of 64? That is 8. So instead of going through this process, what I'm trying to encourage is that you can do it directly. What is 4? 4 is 2 times 2. That is 2 squared. Then I'm going to have 2 raised to power 2 multiplied by 3 all over 2 that we have initially. So these 2 can take care of these 2. At the end of the day, we are going to get 2 raised to power 3. What is 2 raised to power 3? 2 in 3 places. That will be 2 times 2 times 2, and that is going to be 8. And that's what we are going to get. So these are the 7 laws of indices that we discussed yesterday. So I will just give some examples on indices before I will go to simple exponential equations. For instance, let's say example 1. If you are to simplify, let's say simplify the following. So if you asked to simplify what we have on the board, let's say a 27 raised to power 1 over 3. Then b, let's say we have 125 raised to power minus 2 over 3. Let's start with this solution. This first one now, of course, is talking about the cube root of 27. We are talking about the cube root of 27 here. So if this is the cube root of 27, of course, that will be the cube root of 27. Then the cube root of 27 is 3. Or, that's why I said we shouldn't be too rigid about the law. I can change 27 to 3 in 3 places, because 3 times 3 is 9, 9 times 3 times 7. So I will change 27 to 3 raised to power 3 multiplied by what we have here. So this can take care of this. And at the end of the day, I'm going to get 3 raised to power 1, which is equal to 3. So either way, it's either you find the cube root of 27, or you just express 27 as index of 3. Then you work it out directly. So that is what you are going to get. You are going to get 3. Then the second example. This second example now, The solution to the second example is where you have 125 raised to power 2 all over 3. Of course, if you have this type of problem, just concentrate on the denominator of the power. In this case now, we have 3. Just look at the base, what you are given. Can you express that base as cube of something, of a particular digit? That should be the thinking. Then if the response is yes, then as what? Like I have 125 here. 125. Of course, what first comes to my mind is that it can be index of 5 raised to power something. And if that is the case, then I can just, you just have to think, what is 5 times 5 is 25. 25 times 5, that's 125. So I can change this 125 to 5 raised to power 3. Multiply by minus 2 all over 3. This can take care of this. Then at the end of the day, I'm going to have 5 raised to power minus 2. And this same thing as 1 all over 5 raised to power 2. And this same thing as 1 all over 25. I decided to do this directly. But if you don't want to do it directly, this is what you can also do it using the law. Then what are you expected to do? You first find the cube root of 125 raised to power minus 2. So if you find the or you can find the cube root of 125, or you first rewrite this as you can. We can actually write this and say this is the same thing as 1 all over 125 raised to power 2 over 3. Because for us to be able to remove the negative, we change it to reciprocal. For us to be able to remove the negative, we change it to reciprocal. For us to be able to remove, we change this to reciprocal. So if this is the case, then I can change this to 1 all over, then 5 is the cube root. That will be the cube root of 125 squared. So, of course, we know that the cube root of 125, everything squared. The cube root of 125 is 5. Then I'm going to get 1 all over 5 squared. And that's the same thing as 1 all over 25. So it's still the same thing. Irrespective of the approach, just make sure that you approach this problem with open mind. With open mind and confidence that you can do it. So let's consider another example. Example 2. Simplify. We also simplify. We do some simplification here. So we are going to simplify further. We simplify the following: is 0.027 raised to power 2 over 3. Then let's take another one. Probably when we have, okay, like the example 3 I gave yesterday that we are unable to solve. 2 raised to power s raised to power half multiplied by 3 raised to power s raised to power minus 5 all over 2. Let's quickly look at this. Under the second example A, we have is 0.027 raised to power, everything raised to power 2 all over 3. So what are we expected to do here? Of course, this is a decimal fraction. Then if you want to solve this now, we can change that decimal fraction to the normal fraction. How do we do that? Just shift this decimal to the back of the last digit. That's how many times are we going to do that? 1, 2, 3. So instead of 0.0227, I will change this to 27 all over. We shifted the decimal point 3 times. Then that will be all over 1,000. Everything raised to power 2 all over 3. So let's look at this critically. As I've said earlier on, concentrate on the denominator. Let's check what we have inside the bracket. Can we express both the numerator and the denominator as index of a particular digit raised to power 3? The answer is, in this case, is yes. Look at the numerator, 27. 3 in 3 places is 27. So I will change that 27 to 3 raised to power 3 divided by, let's look at the denominator, 1,000. 1,000 is 10 raised to power 3. Then everything raised to power 2 all over 3. Okay? So if the numerator, the power at the numerator is 3 and the denominator is also 3, we can express this as just say 3 all over 10. Since everything is raised to power 3, 3 multiplied by 2 over 3. Then 3 can take care of this 3. So this 3 can take care of this. Then from there now, I'm going to get 3 all over 10, everything raised to power 2. And this same thing as you saying 3 squared all over 10 squared. Then if that is what you get, then what is 3 squared? 3 squared will be 9, while 10 squared will be 100. And that will be our final answer. So whenever you have questions under indices, just think about what to do and how to express your answer. Then the second example, under example 2, is where we have 2 raised to power s, 2x raised to power half multiplied by 3x raised to power minus 5 all over 2. Please, let's look at this. You know, the law of indices that we are talking about has nothing to do with this, with these digits 2 and 3, which is this digit now is the coefficient. In this case now, this 2 is the coefficient of s raised to power half, while this 3 is the coefficient of s raised to power minus 5 all over 2. So we can bring up the coefficients, then concentrate on what we are given. That is, I would say 2 times 3. Bring everything out into brackets. Then what do we have left? S raised to power half multiplied by s raised to power minus 5 all over 2. So this is the third example that I gave in the first class. 2 times 3 is what? Is 6. Into brackets, we can go ahead and apply the law of indices here. The base are the same. The operating sign is multiplication, so we go ahead and add. I'm going to have half plus minus 5 all over 2. I'm just trying to do this stepwisely. You understand? Then I'm going to get 6 into bracket s raised to power half plus times minus is minus 5 all over 2. That's what we get. Then if we simplify further, we are going to get 6 into bracket s raised to power. When you find the LCM, of course I can write the answer directly, but just to fulfill all righteousness, let me just do it stepwisely. The LCM is 2, so 2 into 1, I'm going to have 1 minus 5 here. When I take the LCM, at the end of the day, I'm going to have 6 into bracket s raised to power 1 minus 5, that's minus 4 all over 2. So 4 divided by 2 that's 2. Then I'm going to have 6. I can remove the bracket now. S raised to power minus 2. And that is what we are going to get. So if we get this, I can leave the answer like this, or I simplify further. I just say 6 all over s raised to power 2. So that will be the final answer. So we have been able to consider 2 examples on this. Then I would love to take another example. Example 3. Let me call that example 3 before I will introduce simple exponential equations. And of course, you can just go to, we have many textbooks, just visit textbooks and practice question on indices, law of indices. And if you come across anyone that seems difficult, that you can't handle, then you can just put it in the comment section. I promise to check the comment section, then solve the problem. If you're unable to solve it, I will do that for you. Then let's take example 3. This will be the last example that I'm going to take under the law of indices, indices before I go to simple exponential equations. So let's see this example. Simplify. What do we want to simplify? We want to simplify 6s cubed y raised to power 5 all over 2 z raised to power 1 all over 4 all squared divided into bracket 9 s raised to power 6 y quarts z cubed into bracket half. This is what we want to do. Into bracket half. Of course, the first step is that this square is common, and this is raised to power. This is like saying square root of what we have here. So what do we do here? Of course, I can decide to open up. That is, we don't have a particular approach to a given question in mathematics. It depends on the discretion of the person solving the problem. So I may try to use a particular approach now. This same question, somebody can approach it with another method, but we must have the same answer at the end of the day. This is how I want to approach it. I want to open up this bracket. That is, I want to take the square from that square, from that third law of indices. It permits us to be able to use these 2 to multiply each of these power. You understand? That is, I'm going to get 6 squared s raised to power 3 times 2 y raised to power 5 all over 2 multiplied by 2, then z 1 all over 4 times 2. So from that third law of indices, we are permitted to do this. Then divided by everything, I've been able to use these 2 now, the square here, the power outside, to multiply through all over. I'm going to use this half also to multiply through that, and then I will have 9 raised to power half, then s raised to power 6 multiplied by half, y raised to power 4 multiplied by half, then z raised to power 3 multiplied by half. That's what I'm going to get here. Then if that is taken, I can go ahead and simplify further. Then 6 squared gives what? 36. This gives you s raised to power 6. Then this will take care of this. I will have y raised to power 5, here 1, here 2, and I'm going to get z raised to power half. That is what I'm going to get. Divided by, in this case now, I can change 9 to 3. I will have, in this case now, I'm going to have, instead of 9, I want to change it to 3 raised to power 2, multiplied by half. Then here, I'm going to get s raised to power, here 1, here 3, s cubed, then here 1, here 2, y squared, then z raised to power 3 all over 2. That is what I'm going to get. So if I simplify further, I'm going to get, in this case now, we can handle it separately, and I can decide to do this to cancel this. So at the end of the day, I'm going to get 36. S raised to power 6, y raised to power 5, z raised to power half. Of course, division, I can introduce division line to have 3 s cubed, y squared, then z raised to power 3 all over 2. 3 can reduce this to 12. Okay, so let me clean this so that we'll be able to simplify further. If that is the case, this is what I'm going to get to. I'm going to get 12. I will have 12. Then this is division. So under x now, I'm going to get 12 s raised to power 6 minus 3. Because if you look at the second law, when we have division, we subtract. Then y raised to power, this is 5 minus 2. 5 minus 2. Then we have z raised to power half minus 3 all over 2. That is what we are going to get from there. Then if you simplify further, we are going to have 12 raised to power s raised to power 3, y raised to power 3, 5 minus 3, then z raised to power half minus 3 all over 2. That will be minus 1. So I want us to look at it critically. Then I can write this as 12 raised to power s cubed, y cubed all over z, and that will be the final answer that we are going to get from this question. So at least so far we have been able to consider 3 examples. The first example is 2 in 1, A and B. The second example, A and B. And this last example, this is actually one question. So we have been able to address some problems under indices. So with this, I just want to shift focus to what we call simple exponential equations. So from the word exponential, when I introduce, okay, let me just recall what I said yesterday. So let's look at exponential equations. So exponential equation can be reduced to quadratic form. So what we do under this simple exponential equation is that we can reduce them to quadratic form in most cases, and it can even be in linear form, but we can actually reduce them. So these simple exponential equations actually involve problems under logarithm, under indices. That is, if you have something like, when I introduced in the topic, I said when you have s raised to power 4, this 4, I said you can call it exponent. It can be referred to as exponent or index or power. So from this subtopic that I introduced now, I call it can be called simple. Let me just put the word simple so that people will not think it's something that is complex. Simple exponential. If I don't want to call it exponential equation, I can call it indicial equations, because this is just a system of naming ceremony. If you want to use exponent here, if you want to refer to exponents, then we can call it simple exponential equations. If I want to refer to 4 as index, then I can call this simple indicial equations. You understand? So this is just it's very simple. What are we talking about? We are just talking about equation that involves exponents. That's what we are talking about. So let me just use example to introduce this simple exponential equation. Let's say example. Let's say example 4. We can say, let me say, solve the equations. I will start with simple equations. The first one, 4x is equal to 0.5. Then let me introduce another simple one where I have 9x is equal to 1 all over 729. So let's concentrate. This first one now, I have what? 4x is equal to 0.5. So, this one is different from 4 raised to the power x is different from 4x. So, had it been what we are given here, if what we are given here is 4x is equal to 0.5, of course, every one of us know what to do. Just say divide both sides by 4. This will cancel this. Then x, 0.5 is half. Then x will be equal to 1 all over 8. We just get our answer directly. But in this case now, it's not 4x, it's 4 raised to power x. So what do we do here? How do we approach this here? Then this is what we do. Can I express 4 as an index of a particular digit? Yes. What is 4? 4 is 2 squared. Then I'll change this to 2 squared in 2 raised to power 2 into bracket x. Then I can change half, 0.5 to half. That is, if I shift this one once, that will be 5 all over 10. Here 1, here 2, that will be half. Then 4 is same thing as 2 raised to power 2. Of course, everything raised to power x. Then from the third law of indices, this will be what? 2 raised to power 2x. And it will be equal to half. Of course, I can write this half. Please, I want us to concentrate. It's very simple. So that at the end of the day, I will have 2 raised to power 2x to be equal to 2 raised to power 1. 2 raised to power minus 1. That is half. Half is 2 raised to power 1. If I want to write it in the negative form, we are going to have something like this. Now look at the base are equal. If the base are equal, we equate the power, and it's vice versa. If the powers are equal, you equate the base. Do we get that? When you are solving simple exponential equations, if equations involving indices, if the base are equal, you equate the index or the power, and if the power are equal, you equate the base. It's vice versa. So in this case now, the base are equal. We now say therefore 2x is equal to minus 1. Therefore x is equal to minus half, and that's what we get. So that is what we are going to get. Then the second question that we are given, that B part of the example 4, is where we have 9x is equal to 1 all over 729. So how do we approach this? Of course, look at this 729. Can we rewrite this 729 as index of a particular digit? Yes, from this word 9, it shows that 9 multiplied by 9 multiplied by something, we can actually have 729. Then 9 in 3 places, we actually give us this, because 9 times 1 is 81. 9 times 1 is 81. Then 81 times 9. 9 times 1, 9. 9 times 8 is 72. So I can change 9x. I can change this to 1 all over 9 raised to power 3. Then I can move this up. I will have 9x to be equal to 9 raised to power minus 3. From that, from the law of indices, this is the negative form of writing this. And if I have this, I can change it to this. Then at this point also, the base are equal. Once the base are equal, you equate the power. Therefore, s is equal to minus 3. So we have been able to solve the first example. Then let me introduce another example. Though it's simple, but we have to be very careful. So let's see example 5. Example 5. Example 5. Solve the equation. Solve the equation. For instance, if you have something like 2x plus 2 raised to power minus x is equal to 2. So how do we solve this type of problem? Of course, for us to be able to do this, we must have vast knowledge of indices. It's because it's exponential equations. It's not the normal equations that we know. So this is what we do. I can change this to 2x plus 2 raised to power minus x is equal to 2. So let me rewrite this. That is, I will have 2 raised to power x plus 1 all over 2 raised to power x. That is this negative form. I can write this as this, and it's equal to 2. But looking at what we have here, we cannot solve this directly. Then we can use lets and recurse statements. That is, I'm going to represent this 2 raised to power x as, I can use another variable to represent this. After I will solve it, get the value of that variable, then I will now recall to be able to solve this. So when we have this simple exponential problem, what we normally use is to we use what is called the let and recall process. That is this what I say. I will say let maybe p to represent 2 raised to power x. So if p is represented as 2 raised to power x, then I will now change this. Instead of 2 raised to power x, I'll change this to p plus 1 all over p is equal to 2, this over 1. Then from there, if you look at the left-hand side, when we look at the left-hand side, I will take the LCM. The LCM will be P. 1 in P will be P. P times P, I'm going to get P squared. Plus P in P, that is 1. 1 times 1, that is 1, is equal to 2. From here now, I can cross multiply. That is, I will have P squared plus 1 equal to 2P. I will bring everything to the left-hand side so that I can have 0 at the right-hand side. So I'm going to get P squared minus 2P plus 1 equal to 0. And as we have it on the board, this is what is this what we have here. What we have here now is now a quadratic equation. And if you have quadratic equation, of course, we know that we have about 3 methods if you want to solve it without using graph. So is there, once we arrive at this point, is that you apply factorization method, the formula method, or completing the square. But when we look at this equation now, this equation is factorizable. We can actually factorize it. Then let me go ahead and use factorization method. So in this case now, I'm going to have P squared minus P plus 1 equal to 0. So I'll do the grouping. What is common in this first bracket is P. So that I have P minus 1. Then if you check the second bracket, what is common is also minus 1. Then I'm going to have P minus 1 equal to 0. So if you apply factorization method to quadratic equation, this is one way or one method to know that what you are doing is right. What you have in the first bracket must be the same thing that you have in the second bracket. So you just pick it once, P minus 1. Then you now group these two together. In this case also we have P minus 1 equal to 0. Then we have two factors equal to 0. So that simply means that it's either the first factor equal to 0 or the second one, P minus 1 equal to 0. So if we get this now, if P minus 1 is equal to 0, then P can be equal to 1 or P is equal to 1. So in this case now, P is equal to 1 twice. So the two roots of the equation is 1. In this case, the two roots of the equation is 1. But if you but from the onset, we have to find X, not P. But because we cannot get P directly, we use a let statement. We now recall, once we have gotten the value of Y, we now recall that P is equal to 2 raised by X. That was the assumption when we started. So we have to recall because we have to find X, not P. But since we cannot get X directly, that's why we use the let statement. So we recall now. Then, of course, in this case now, in this particular question, P is 1 twice. So we now say P is equal to 1. In this case, you understand? What is P? P is not 2 raised by S. We now say 2 raised by S is equal to 1. Then from that fourth law of indices, we said anything raised by 0 is 1. So I can, in this case now, I can change this 1 to be equal to 2 raised by 0 because it is 2 that is my base here. And I needed to get it. So I will now say, therefore, 2 raised by S is equal to 2 raised by 0. The base are equal, equates the power. Therefore, X is equal to 0. And that will be the answer. So look at this example 5. We can never get it directly. If we don't use the let and recall process, we can't get it directly. And that is how to solve simple exponential equations. So let me introduce one more examples under this. Then we close for the day. Solve the equation. Solve the equation. Let's look at the equation. Okay, let me pick this. 5 raised to power 2x. 5 raised to power 2x plus 1 is equal to 26 into bracket 5 raised to power x minus 1. Look at this. This question, though you might think it is difficult, but it is not. Just apply the laws of indices, use the let and recall process, then we are going to get the answer. What do we do? Just look at it. We are given 5 raised by 2x plus 1 equal to 26 into 5 raised by x minus 1. This is what we do. You know, I can rewrite this. I can rewrite what I have here as 5 raised by s, everything raised by 2. Just go through the law of indices and understand it perfectly. There's a particular law, I think the third law, that says if you have s raised by a, everything raised by b, it's same thing as s raised by ab. So if we apply that law now, I can split this. Plus, this is just 1. It's equal to 26 into bracket. Look at the second law of indices says that if the base are equal and the operating sign is negative, the law says that we should subtract the power. But in this case now, we have it here. I can split it as this, as 5 raised by s divided by 5 raised by 1. If I'm giving something like this, If I have to solve this, I'm going to get this because the base are equal. The operating sign is division. Then I'll subtract the power. I'll just subtract the power. But if we are not given in this form, you should be able to rewrite it in this form. That is why it is compulsory. And don't let me use the word compulsory. It is necessary to understand the laws of indices very well for us to be able to solve any problem. You should be able to solve any given problem under indices or simple exponential equation. In some textbook, they can be referred to as simple indices equations. So at this point now, I can write this as 5 raised to power x all squared plus 1 is equal to 26 into brackets. This is division into brackets. 5 raised to power x all over 5 is still the same thing. So I will now say I can use y. It's not compulsory I use p. I can use another letter. P. Let y is equal to 5 raised by x. So if you use that let statement now, then what is the implication here? If this is what we assume, then wherever I have 5 raised by x, I'll change it to y. So that simply means that I'm going to have y squared plus 1 is equal to 26 into brackets. The numerator, I will change it to y all over 5. This is what I'm going to get. Then from here, I'm going to get y squared plus 1 is equal to 26y all over 5. From there, I can cross multiply to get 5 multiplying y squared plus 1 is equal to 26y. So that's what we are going to get. If we get that now, I can bring everything together. I will say 5y squared. If this minus 26y comes in, it attracts a negative sign. We all know that if this crosses the equality sign, the sign will change. If you have it to be negative here, by the time it crosses this equality sign, the sign will change to negative. And if it is positive, it change to negative. And if it is negative, the sign changes to positive. So here now I'm going to have minus 26y, then plus 5 times 1, 5 is equal to 0. At this point also, we have been able to derive a quadratic equations. And this quadratic equation is factorizable, so we don't need to use either formula method or complete this equation. So I will go ahead and factorize this. So this will give me 5y squared. How do we factorize them? Just don't let me assume. If you want to use factorization under quadratic equation, multiply the coefficient of y squared by the constant. 5 times 5 in this case will be 25. You now think, you look at the two factors of 25. That's going to give us minus 26. So there are so many factors of 25. Maybe 25 times 1 is a factor. 5 times 5 is a factor. Minus 21 times minus 1 is a factor. Minus 5 times minus 5 is a factor. But you look for the suitable factors, two factors that are suitable that will give us this. In this case now, if you have 25, the suitable factors in this case will now be minus 25 and minus 1. Minus 25 times minus 1 is 25. But minus 25 plus minus 1 is minus 26. So that's what. So I will now split this minus 26 into minus 25 minus y. That is, this will be minus 25y minus y. Of course, there's nothing like 1y. So one is unity. So it's a unit. We don't need to put it here. So minus 25y minus y gives minus 26. So under factorization, we just try to expand so that we can do the grouping. So what is common in this first bracket is 5y. Then we are left with y minus 5. What we have here is minus 1. That is common. Then we are left with y minus 5 equal to 0. Like what you have here is what you have here. So you pick it once, y minus 5 into bracket 5y minus 1 equal to 0. Then when we have the product of two factors to be equal to 0, the implication is that the first factor equal to 0 or the second, at least one of the two factors must be equal to 0 for us to be able to get 0, but we are not sure. So we now say y minus 5 equals 0 or 5y minus 1 equal to 0. In this case now, y, you transfer this minus 5 to the other side, the sign will change, equal to 5, or you say 5y is equal to 1. So y is equal to 5, or in this case now, divide both sides by 5. This will cancel this, 1 all over 5. These are the two. In this case now, we have two different values for y, but we have to find x, not y. We now recall. You recall that y is equal to 5 raised per x. So when in this case now there are two distinct values for x and for y, so we must do it separately. When y is equal to 5, what will happen? We are going to have 5 now is equal to 5x, right? This is 5 raised to power 1. The base are equal, equate the power. Therefore, x is equal to 1. We have gotten one value for x. Then we do the second one. When also when y is equal to 1 all over 5, that's the second value, right? The second value is 1 all over 5. What will happen? Y is equal to 5 raised per x. So here we have 1 all over 5 is equal to 5 raised per x. If that is the case, then I can write it as 5 raised per minus 1 equal to 5 raised per x. So the base are equal, you equate the power. Therefore, x is equal to minus 1. Then we now conclude that x is equal to 1 or minus 1. And that is how to solve simple exponential equation. So far, I've been able to do the recap of the first class that we did under indices, the lots of indices, and I gave example. Thereafter, I introduced simple exponential equations, and I said you can, in some textbook, you can see it as indicial equations. So we have been able to solve about 3 examples under simple exponential equations using the let and the recall process, because you cannot solve simple exponential equations directly because of the power, but we can represent it as, if you are given the problem in form of x, you can use any other letters of the alphabet except from that x. You can call it p, you can call it a, you can use any other letters. At the end of the day, we are able to solve about 3 examples under simple exponential equations. So I would love to stop the class now. So if you have any further problems on simple exponential equation, just type it in the comment section. I promise to attend to it. So by the grace of God, in our next class, I will introduce logarithm. Then we talk about logarithmic equations, and we talk about logarithmic equations. We'll be able to solve that. And I want to encourage you that you should subscribe to my YouTube channel, Toyded Online Class, so that we'll be able to discuss so many problems together, and we will be able to finalize. So I want to thank you for your time, and I want to say bye for now.